Hi everyone, it's Anna, and here we're gonna work out on an example to see how derivatives of a function gives us information about the function. Our problem at hand is, as you can see, this function, and we want to answer the following question. The first question is where f is increasing or decreasing. And we're gonna learn that where f is concaving up or down, and where are the local minimums or maximums of f, and where f change curvature. In order to answer this question, we first compute the derivative, the first derivative. Let's say, sorry, first derivative f prime of x equal minus 3x squared plus 3x plus 18. And to simplify this, we factor minus 3, we get x squared minus x minus 6. And we can write this as product of x minus 3 times x plus 2. So writing it this way, immediately we find out the solution of f prime equals 0 would be x equal 3 and x equal minus 2. Okay, now in order to find out where our function is increasing or decreasing, we look at this. Let's compute our derivative at 0, which is at this interval. At this interval, the 0 is like here. At 0, we would get minus 3 times minus 3 times 2. So the derivative would be positive at this interval. At this interval, let's compute derivative at, let's say, minus 3. We would get minus 3 times minus 6 times minus 1. So at this interval, the derivative is negative. Also at this integral, we will see that the derivative is negative. So our function is decreasing at this interval, it's increasing at this interval, and again decreasing at that interval. So, and we know that because we compute the zeros of derivative, we already know that our local minima or maxima would happen at these points. But we further will specify at which is maxima, at which is a minima. Now let's compute the second derivative. We will get that minus 6x plus 3. Therefore, setting 0, setting the second derivative 0, we would reach that x is equal 1/2. So now we are going to see how the concavity is at each of these intervals. So at this interval, we have like 1 here, we impute 1 at our function. If we put plug in 1 at our second derivative, we get, let's say, which is negative. So at this interval, we get negative second derivative, and at this interval, we get positive second derivative. Now putting all these points together, we have 1/2, we have 3, and we have -2. We know that, and let's separate them by this line. Okay, we know that the second derivative is positive for values less than 1/2. So the second derivative is positive here, it's positive here, it's negative here, and it's negative here. And our first derivative is positive between two roots, which is here, and it's negative here. So at the interval -infinity until -2, our function having a positive second derivative and a negative first derivative, it means that it's decreasing, but it's concaving up. So at here we would approximately have something like this. Then at -2 we have the local minima, because the function is decreasing before -2 and it's increasing after. Sorry. So we're gonna have something like this. At 1/2, we know that our concavity would change, so the curvature would change. Instead of concaving up, it would concave down. Again, at +3, we have and we see that our second derivative is also negative, so we would be concaving down, and our function is increasing. So here we would get a local maxima. So, and then again, here we have a negative second derivative, which means that we are concaving down, and a negative first derivative, which means that we are decreasing. So our function would look like something like this. Only by examining the first derivative and second derivative and finding the intervals in which each of them are positive and negative, we could say that if the function is increasing or decreasing in that interval, or if the function is concaving up or down, and determining whether we have a local minima or local maxima.